There are regions in the solar system that announce themselves with bright surfaces and familiar names. And then there are regions that stay quiet for so long that astronomy has to infer them before it can truly see them. The Kuiper Belt belongs to that second kind. It is not a wall at the edge of everything, and it is not a neat row of little frozen worlds keeping orderly distance from one another. It is a broad, cold remnant beyond Neptune, a place where the solar system left behind a record of how it formed, how the giant planets moved, and how small icy bodies survived by never quite becoming full planets. It is a region defined as much by disturbance as by stillness. Neptune shaped it, stirred it, trapped some objects into repeating rhythms, flung others outward, and left a quieter population in orbits that seem to have preserved a memory of earlier times. Even now, the belt is not entirely at rest. Bodies collide. Dust is made and lost. Some objects are nudged inward and eventually become comets. The frontier looks calm from far away, but the calm is built on a long history of motion. And tonight, we will follow that history gently, one quiet clue at a time. Why, hello there and welcome in. I'm Madeline Rowe, and tonight we're drifting out on a long, slow journey beyond Neptune into the science of the Kuiper Belt. And if you'd like more calm, evidence-based case files like this one, subscribe, and you'll always have another waiting for you. Back in my office, the room has taken on the kind of order that only appears simple at first glance. The lamp on my desk casts a warm circle of light over the centre, but most of the room lies farther out, dimmer, colder, and less evenly arranged. A line of folders curves along the shelf instead of sitting square, and between them are small gaps, crowded spots, and one drawer that never quite shuts the same way twice, as though something larger has tugged at the whole arrangement in the past and left its influence behind. Near the edge of the desk, there is a scatter of paper clips and ticket stubs and penciled notes that never turned into anything grand, but never disappeared either. They are leftovers, really, but leftovers with a story. Beyond the reach of the lamp, the room feels wider than it is, full of objects that are not random, only hard to classify until you stand up and look from the right angle. That is what the Kuiper Belt feels like to me tonight. Not an empty margin, but the outer filing cabinet of the solar system, where old motions are preserved in cold storage and small worlds still keep the record. The file on my desk is thick in an understated way. No dramatic warning stamp, no oversized headline, just a label with 3 plain words: the Kuiper Belt. It sounds almost too tidy for what it contains. The name suggests a simple belt, a narrow strip, perhaps a clean boundary at the edge of the planets. But the more closely one reads, the more that word begins to feel like a convenience rather than a perfect description. The Kuiper Belt is broader, thicker, and more textured than the term implies. It is a region of icy bodies beyond Neptune, mostly occupying the outer solar system from just beyond Neptune's orbit into a broader domain that shades into the scattered disk. Its inhabitants vary in size, brightness, colour, orbit, companionship, and history. Some travel on remarkably calm, nearly circular paths. Some are locked into repeating gravitational rhythms with Neptune. Some have been scattered onto elongated, tilted tracks that send them far above and below the plane of the planets. Some have moons. Some may be binaries, or contact binaries, or fragments of ancient collisions. A few are so large that they forced astronomy to rethink its categories. If one wanted the short version, one could say this: the Kuiper Belt is one of the solar system's surviving populations of early building material, preserved beyond Neptune in the deep cold. But that short version leaves out what makes it such a beautiful case, because this region is not only old, it is sculpted. It is not only full of remnants, it is organized by history. The shapes of its orbits, the clustering of its populations, the existence of resonant bodies, the quieter classical objects, the scattered and detached worlds, all of it points back toward a solar system that did not form in a single settled pose and stay there. The giant planets moved. Their gravity reworked the outskirts, and the Kuiper Belt became less like a forgotten pile of debris and more like a fossilized record of migration, resonance, collision, and survival. Before astronomy could point telescopes at a confirmed population of worlds beyond Neptune, it first had to suspect that something was missing from the story of comets. That is one of the most appealing things about this case. The Kuiper Belt was not discovered all at once because someone looked in the right place and happened to see it. It was partly predicted from a dynamical problem. Long before modern surveys found object after object beyond Neptune, astronomers were trying to understand where comets came from and how different comet families might be supplied. The long-period comets, arriving from all directions on highly stretched paths, pointed toward a distant spherical reservoir, what became known as the Oort cloud. But short-period comets, especially those on prograde, low-inclination orbits that stay closer to the plane of the planets, seemed harder to explain if they all began in that distant spherical cloud. That gap in the story created room for a new idea. In the mid-20th century, Kenneth Edgeworth argued that the solar system's original material should not simply stop at Pluto's distance, but should thin outward, leaving a region where small bodies could form and persist. Gerard Kuiper, working from different concerns, also connected comet formation to the outer solar system, though the historical naming is a little untidy, as histories of science often are. Edgeworth's contribution was important. Kuiper's name became attached to the belt, and the modern phrase stuck. There is something very fitting in that. Even the name of the Kuiper Belt has a slightly scattered orbit of its own, carrying traces of prediction, oversight, and later recognition. For a long time, though, the belt remained an informed suspicion. Theoretical work in the late 20th century sharpened that suspicion considerably. Numerical studies showed that the observed short-period comets were not comfortably explained as simple descendants of the isotropic Oort cloud. Their parent population seemed likely to be flatter, more orderly, more solar system-like in its geometry. Somewhere beyond Neptune, there appeared to be a source region waiting to be seen. But suspicion is not detection, and astronomy still needed both technology and patience. That is where one of the lovelier parts of the story enters. The discovery of the first confirmed object beyond Pluto that truly belonged to this broader population did not happen in a single glamorous sweep. It took years of searching. David Jewett and Jane Liu conducted persistent surveys for faint, slow-moving objects in the outer solar system, watching for tiny motions against the fixed-looking background of stars. The objects they sought would be dim, distant, and deliberate. In 1992, that patience paid off with the detection of 1992 QB1, the first recognized Kuiper Belt object beyond Pluto. The discovery was not merely the finding of one small world, it was the opening of a region. Once one such body had been found, others followed. and the idea of a trans-Neptunian population shifted from theoretical possibility into observed architecture. That change matters for the mood of the story. Before 1992, the Kuiper Belt was largely a hypothesis about what ought to exist if the mathematics of comets and planet formation were trying to tell us something true. After 1992, it became a place, not a fully mapped one, not a neatly understood one, but a place all the same. Pluto, which for decades had stood as an odd, solitary outer body, suddenly looked less alone and more like the first known member of a larger, colder community. It is one of those moments in science that changes not just the facts, but the shape of the question. Pluto did not vanish from importance. It changed context. Now, if we set history aside for a moment and simply ask where this region is, the answer begins plainly enough. Neptune orbits the Sun at about 30 astronomical units, with 1 astronomical unit being the average Earth-Sun distance. Beyond that orbit lies the broad domain that we call the Kuiper Belt. The main classical region runs outward to around 50 astronomical units, though the system does not end cleanly there. Beyond the main body lies the scattered disk, extending far farther out, with some objects travelling hundreds of astronomical units from the Sun at the most distant parts of their paths. So when people speak of the Kuiper Belt, they may mean the main belt in a strict sense, or they may mean the larger trans-Neptunian environment whose populations overlap in origin and influence. Either way, the geometry is not a thin ring like a line drawn by a compass. It is better pictured as a puffed-up outer disk, a broad, cold zone of bodies with real thickness and variety. This is one of the first useful corrections to the mental image many people carry. The asteroid belt, though also not a tightly packed traffic jam of rocks, tends to be pictured as a somewhat flatter population between Mars and Jupiter. The Kuiper Belt is thicker, both physically and dynamically. It is not evenly filled, and it is not populated by bodies moving in a single flat sheet. Some objects remain fairly close to the plane in which the planets orbit, but others are tilted and elongated, with paths that carry them significantly above and below that plane. The farther astronomy looked, the more it became clear that the outer solar system was not simply padded with extra rubble. It had structure. Structure in this case means that the distribution of Kuiper Belt objects is telling us something. Orbits are not random. Bodies group into populations. Certain resonances are heavily occupied. Some regions are more crowded than older, simple models might have expected. There is a relatively sharp decline in the main classical population beyond the outer part of the belt, sometimes called the Kuiper Cliff. There is also a calmer concentration near the middle of the classical region that hints at delicate early history rather than chaos alone. The belt is not just there, it is arranged. An arrangement in celestial mechanics is seldom accidental. The outer edge is worth lingering on, because people often imagine the Kuiper Belt fading away smoothly, as though the solar system simply grows thinner and thinner with distance. But the main classical belt seems to show a more noticeable drop in objects beyond roughly 50 astronomical units. That drop, imperfectly named the Kuiper Cliff, has been one of the most intriguing boundaries in the outer solar system. It does not mean that nothing exists beyond it. Clearly, plenty does. Scattered and detached objects travel far beyond that distance, but the comparatively abrupt thinning of the main belt suggests that some process or combination of processes marked the outer distribution of objects more sharply than one might have expected from a featureless disk. Why should there be such a drop? There are several ways to approach that question. Perhaps the original planetesimal disk did not extend outward with equal efficiency forever. Perhaps the conditions for building or preserving objects changed with distance. Perhaps Neptune's migration and resonance sweeping affected where long-term stability could remain. Perhaps later depletion removed much of the outer material that once existed there. The important thing, for our purposes, is not to force the edge into a single overly simple explanation. The important thing is to notice that the Kuiper Belt is not a vague smear of leftovers. Even its emptier regions are informative. The absence of expected objects can be as revealing as the presence of unusual ones. To see why, one has to return to the role of Neptune. Neptune is, in many ways, the detective's recurring suspect in this file. Not because Neptune destroyed the belt exactly, but because Neptune shaped nearly every major clue we use to understand it. Current models of solar system evolution indicate that the giant planets did not necessarily form and remain on the exact orbits they occupy now. In the broad picture, the early solar system included the Sun, a gaseous disk, the forming giant planets, and a far larger mass of small icy bodies in the outer regions than we see preserved today. As Jupiter and Saturn interacted gravitationally, and as the giant planets exchanged angular momentum with the surrounding disk of planetesimals, Uranus and Neptune drifted outward. Neptune, being the outermost giant planet, moved through or near a reservoir of small icy bodies. The outward migration matters because gravity is not merely a pulling force, it is also a sorting mechanism. As Neptune migrated, it scattered some bodies, trapped some into resonances, stirred the inclinations and eccentricities of others, and left behind a quieter classical population in regions where its influence was weaker or more indirect. In that sense, the modern Kuiper Belt is not simply the untouched leftover from solar system formation. It is a leftover that has been edited. The edited state is the evidence. One can look at the range of orbital types and see traces of Neptune's movement recorded in them like grooves on an old disk. It helps, sometimes, to picture the young outer solar system not as a finished display, but as a workshop before the tools have been put away. Bodies large and small are still interacting. Gravitational kicks accumulate. Paths that seem fixed in a textbook are still negotiable. The planets do not have to move quickly to have large consequences. A slow outward migration by Neptune over long spans of time is enough to shift resonances across broad regions, capturing some bodies and destabilizing others. In human terms, it would feel like furniture moving on its own, so gradually that you notice only when you return years later and realize the whole room has been rearranged. The simplest place to begin within this architecture is the classical Kuiper Belt. These are the bodies whose orbits most closely resemble what early astronomers once expected from a belt beyond Neptune. Relatively modest eccentricities, not too much inclination, and average distances from the Sun generally between about 40 and 50 astronomical units. But even here, where one might hope for a quiet neighbourhood, the picture divides into two broad categories: cold classicals and hot classicals. The labels are misleading if taken literally. They do not refer to surface temperature, because out there almost everything is cold in the ordinary sense. The words instead describe dynamical calm and dynamical excitement. Cold classical objects occupy relatively circular, low-inclination orbits. They appear to have remained more insulated from Neptune's strongest historical disturbances. Their orbits are more regular, more settled, and probably closer to the original local arrangement of the outer disk. They are, in a useful sense, some of the least jostled residents of the region. Hot classicals, by contrast, have more eccentric and more inclined orbits. They bear stronger signs of past interaction. Something, and Neptune is the obvious something, pumped energy into their motions and left them on less sedate paths. If the cold classicals are the quiet archival boxes in the farthest cabinet, the hot classicals are the folders that were clearly handled, moved, refiled, and perhaps returned to a different shelf. And that difference makes the cold population especially valuable. A great deal of interest in the Kuiper Belt comes not just from the fact that it holds old material, but from the possibility that some parts of it preserve conditions from very early in solar system history, with less dynamical overwriting than other populations. The cold classicals are often treated as one of the best surviving windows into that older state. That raises an even deeper question, one that sits behind much of modern Kuiper Belt science. How did the first small worlds out there actually come together? For a long time, a very straightforward picture was imagined. Dust grains stick, pebbles grow, larger and larger collisions build kilometre-scale bodies, and eventually some regions accumulate sizable planetesimals. But the detailed physics of planetesimal formation is not always so obedient. In many settings, getting from pebbles to robust larger bodies is one of the more difficult steps in planet formation. The Kuiper Belt matters here because some of its quietest objects may preserve clues to that step. If certain cold classical objects formed gently, perhaps through local concentration and soft assembly rather than relentless destructive collisions, then their shapes, binary arrangements, and surface histories could serve as evidence for how the earliest outer planetesimals were born. This is one reason a small object can matter just as much as a large dwarf planet. A world does not have to be geologically elaborate to be historically revealing. Sometimes the bodies that have undergone the least dramatic evolution tell the oldest story most clearly. But quiet does not mean dull. Some of the most interesting objects we have seen up close, or as close as spacecraft can manage, seem to belong to this calmer outer record. When NASA's New Horizons mission flew past Arrokoth after its historic Pluto encounter, it showed us a small Kuiper Belt world that looked astonishingly gentle in its history. Arrokoth's contact binary shape, with two lobes joined softly together, suggested low-speed assembly rather than violent collisional ruin. It was a reminder that not all history is recorded in catastrophe. Some is recorded in the survival of delicacy. Arrokoth deserves a little more time because it offered something rare in Kuiper Belt science, a close view of a modest object that had not been entirely transformed into a spectacle. Pluto astonished by being active, layered, and unexpectedly planet-like. Arrokoth astonished by seeming ancient in a different way. Its form, colour, and apparent lack of severe disruption made it feel like a preserved note from the solar system's opening chapters. It is difficult to overstate how valuable that is. The farther one moves from the sun, the easier it is for old evidence to survive. But survival is not the same as accessibility. New Horizons briefly turned survival into visibility. Then there are the resonant populations, which may be my favourite part of the whole file, because they make the outer solar system feel almost musical. A resonance occurs when an object and Neptune complete orbits in a repeating ratio. Pluto, for example, is in the famous 3:2 resonance with Neptune. For every 3 times Neptune goes around the Sun, Pluto goes around twice. That stable relationship prevents close encounters even though their orbital paths cross in a geometrical sense. Pluto is not a wanderer, barely escaping Neptune's grasp. Pluto is in a carefully timed gravitational arrangement, a repeating pattern that remains stable over very long times. Pluto is not alone there. So many objects occupy the 3-2 resonance that they have their own subgroup name, Plutinos. Other resonances also contain bodies, including the 2-1 resonance and others less well known outside planetary dynamics. These resonances are powerful evidence that Neptune did not simply sit in place while the outer disk calmly accumulated. As Neptune migrated outward, its resonances swept through the trans-Neptunian region like moving shelves, capturing some bodies into repeating relationships and leaving a fingerprint of that migration in the orbital census we observe today. There is something satisfying about that kind of evidence. No one alive watched Neptune migrate. No telescope recorded the process in progress. Yet the belt today contains the residue of those earlier motions in its resonant populations. The outer solar system is full of delayed testimony. A stable 3-2 orbit can be read like a witness statement if one is patient enough to translate gravity into history. Another restful feature of resonances is that they remind us stability does not always mean simplicity. A child might draw planetary orbits as separate neat circles that never touch, and one can understand the instinct. But celestial stability can also emerge from more intricate timing. Pluto's orbit is more eccentric than Neptune's. At certain points, it comes closer to the Sun than Neptune does. Yet because of the resonance and the geometry of the orbit, the two bodies never come dangerously near each other. It is one of those elegant results that feels almost literary. A path that looks risky on paper turns out, through timing, to be safe. Beyond the classical belt and its resonances lies the scattered disk, and the tone changes again. Here we find bodies on much more elongated and tilted paths, objects that can travel far beyond the main belt before returning sunward. These worlds are dynamically restless compared with the quiet, cold classicals. They are thought to have been scattered by Neptune into these stretched trajectories, and some continue to evolve slowly over immense spans of time. The scattered disk is, in a way, the broad halo of Neptune's old interference. It extends the story outward. It tells us that the process of sculpting the belt did not merely rearrange nearby objects into neat bins, it also launched some onto long, eccentric itineraries. The scattered objects are useful partly because they make the outer solar system feel less like a set of shelves and more like a transport system. A body can begin in one region, be reshaped by migration, thrown into a new orbit, spend enormous spans of time in a stretched path, and later perhaps be nudged inward again. In that sense, the Kuiper Belt is not only a population, but a traffic history. Some worlds appear settled. Some are still in long after effects of earlier events. A few objects are even more detached, following orbits that do not come close enough to Neptune for easy explanation by simple present-day scattering alone. Sedna is the famous example, with a perihelion far beyond Neptune and an orbit that reaches astonishing distances from the Sun. Sedna sits in a category of outer solar system mystery that brushes up against questions about passing stars, early cluster environments, or additional unseen influences in the young solar system. For the purposes of our case tonight, it is enough to say that the farther outward one follows these populations, the less tidy the edges become. The Kuiper Belt is not a wall. It grades into broader dynamical territories where the clues remain more ambiguous. And then there are the centaurs, which bring the story inward again. Centaurs travel on unstable paths between Jupiter and Neptune. They do not belong to the Kuiper Belt in the same settled sense as classical or resonant KBOs, but they are widely understood as escapees from that broader trans-Neptunian population, bodies that were scattered inward by Neptune and then handed from giant planet to giant planet through strong gravitational encounters. Their lives in this region are temporary by solar system standards. They are often ejected, broken apart, or pushed farther inward, where some become active comets. So the centaurs form a kind of transit corridor between the cold archive beyond Neptune and the more visible cometary traffic nearer the Sun. This connection to comets is not an incidental feature. It is one of the reasons the Kuiper Belt matters so much. Pieces produced by collisions in the belt, or bodies destabilized by gravitational interactions, can be nudged into new orbits. Neptune begins the process for many of them. Jupiter, farther inward, often takes over as the great corraller and resculptor, shortening their periods and producing what we call Jupiter family comets. These are the short-period comets that helped motivate the belt's existence in the first place. In other words, the Kuiper Belt is not only an outer reservoir of history, it is also a supplier. Some of its contents, after long cold lives in the dark, eventually fall inward and briefly become among the most visible small bodies in the sky. I have always liked that reversal. An object may spend billions of years almost entirely anonymous in the deep outer solar system, and only in its late dynamical life does it acquire the bright tail and public attention of a comet. The showiest phase is the end phase. The quiet beginning lasted vastly longer. Now, if we turn from orbital classes to the bodies themselves, the first thing to say is that Kuiper Belt objects are not all cut from identical material, but they are broadly icy worlds with rocky components, formed or preserved in the cold outer nebula. Water ice is important out there, so are more volatile substances such as methane, carbon monoxide, carbon dioxide, and ammonia, depending on body size, temperature history, and the ability of a given object to retain or lose volatile ices over time. Yet even this simple description requires caution. The Kuiper Belt includes a very wide range of sizes, from small, faint objects only tens of kilometers across to dwarf planets more than 1,000 kilometers in scale. What an object can hold onto, what its surface looks like, how much internal differentiation it may have undergone, whether it ever had enough heat for geologic complexity, all of that depends strongly on size and history. It also depends on distance, sunlight, and time. At Kuiper Belt distances, the Sun is still the Sun, still the central star of the system, but it no longer feels central in the same way. Light there is weak. Warmth is scarce. Surface temperatures remain extremely low. The difference between retaining one volatile and losing another can depend on subtle balances of size, gravity, seasonal orientation, and thermal history over millions of years. A larger body like Pluto can preserve volatile ices and even support seasonal atmospheric exchange. A smaller body may lose the most easily escaped materials and present a simpler, more inert exterior. So the belt is not only sorted by orbits, it is sorted by who can keep what under deep cold conditions. That is part of why surfaces out there can become such useful records. On Earth, weather, water, biology, tectonics, and air erase and repaint constantly. In the Kuiper Belt, change is slower and often quieter. Irradiation by sunlight and energetic particles can darken or redden material over long spans. Impacts can excavate fresher layers. Volatile frosts may shift seasonally on larger bodies. Over ages, chemistry works on the surface in patient ways. The result is that colour and spectrum are not merely cosmetic. They are historical documents written in ice and irradiation. One of the most striking features of the population is its diversity in colour. Some KBOs appear relatively neutral in tone, others are deeply reddish. That redness is usually interpreted as a surface effect tied to irradiation, chemistry, and the long-term processing of ices and organics by sunlight and energetic particles. The surface of an object in the Kuiper Belt is not merely a frozen skin, it is the product of cosmic weathering. Ultraviolet light, charged particles, impacts, possible resurfacing, volatile loss and retention, all of these can alter the visible face of a world over immense timescales. So when astronomers look at the colours of KBOs, they are not simply judging paint. They are reading chemistry, exposure, and history. Size complicates everything further. A small object may preserve a primitive shape, perhaps irregular or even contact binary in form, because its gravity is too weak to pull it into near sphericity. A larger object can become rounder, retain certain volatiles more effectively, generate internal heat from radioactive decay, and support a more elaborate geological past. This is one reason the largest KBOs are so important. They are not merely bigger examples of the small ones, they are thresholds. Once a body becomes large enough, the physics of self-gravity, heat retention, differentiation, and volatile behaviour shifts. Pluto, Eris, Makemake, and Haumea are not just oversized debris. They are laboratories of planetary scale processes in the deep cold. And yet, even the smaller objects can be unexpectedly revealing. Observations over the last few decades have shown that binary systems are not rare in the trans-Neptunian region. In some cases, the two components are of similar size and orbit a shared centre of mass. Some may even touch, forming contact binaries. These arrangements are valuable because they tell us about formation and collisional conditions. A fragile binary, especially one with a wide separation, cannot easily survive a violently crowded environment for billions of years. So when we see binaries, we are learning not only about the objects themselves, but also about the dynamical gentleness or roughness of the region they inhabit. This is especially true for some of the cold classical population, where binaries seem to point toward relatively tranquil assembly conditions early on. A pair of similarly sized bodies orbiting one another in the deep outer solar system has a kind of patience about it. It hints that some parts of the Kuiper Belt were built not only by impact and scattering, but by quieter gravitational courtships, slow enough for two bodies to remain together rather than smash apart or be torn loose. I like to think of binaries as the outer solar system's way of preserving companionship against the odds. In a region defined by distance and faintness, two bodies remain bound, circling one another while together circling the sun. Their existence says something about calm beginnings, or at least calm enough beginnings. Not every pair is primordial, of course, and some systems have more complex histories. But the general lesson holds. If you find a delicate configuration that has survived, you have learned something about the violence it did not experience. Still, the outer solar system was never free of collision. Over long enough times, collisions are inevitable, even in a region as sparsely populated as this one. Some are gentle, some are catastrophic. Small fragments can be produced, surfaces can be refreshed, spin states altered, families perhaps created. In fact, one of the most intriguing examples of collisional history in the Kuiper Belt centres on a world that seems determined to resist tidy classification, Haumea. Before we open that particular folder though, it is worth pausing with Pluto, because Pluto remains the best known ambassador of the Kuiper Belt, even if it no longer stands alone. Pluto's importance is not just historical, it is scientific, emotional, and architectural. As the first body in this broader region to be discovered, Pluto occupied a category all by itself for most of the 20th century. Then the Kuiper Belt appeared around it, and Pluto became the most famous member of a larger population. Later, as additional large trans-Neptunian bodies were found, astronomy was forced to refine its definition of a planet, and Pluto's reclassification followed. Much of the public discussion framed this as loss. In scientific terms, it was really a gain in context. Pluto makes more sense in the Kuiper Belt than it ever did as a lonely outer exception. Its 3-2 resonance with Neptune places it firmly inside the belt's dynamical story. Its complex geology, nitrogen ice plains, mountains of water ice, thin atmosphere, haze layers, and unexpectedly active surface show that the Kuiper Belt is capable of producing worlds of surprising vitality. Pluto is, if anything, the argument against treating the Kuiper Belt as a mere storage zone for frozen rubble. It is a planetary archive, and some archive boxes are far more elaborate inside than their labels suggest. New Horizons transformed that understanding. When the spacecraft flew through the Pluto system, it replaced abstraction with terrain. Suddenly, the best-known KBO was not a point of light or an orbit with a mass estimate. It was a world with Sputnik planitia, layered hazes, and a system of moons that hinted at an energetic and possibly collisional origin. Charon, Pluto's large companion, is especially important here. The Pluto-Charon system is unusually balanced compared with many planet-moon systems. Their shared barycenter lies outside Pluto itself, making them in some sense a binary dwarf planet system. That configuration has long suggested a significant impact in the system's past, and it broadened the conversation about how large Kuiper Belt systems can form. Pluto also taught an important psychological lesson. For years, the Kuiper Belt had been presented mainly through orbital diagrams and small body statistics. New Horizons made clear that these worlds are not merely data points in resonance tables, they are places. Even when we never send a spacecraft to most of them, that change in perspective matters. The belt is a population of worlds, not just a population of objects. Which brings us, naturally, to Haumea, the strangest folder in the cabinet, and one I would never leave unopened. Haumea is one of the large dwarf planets of the Kuiper Belt, but almost every attempt to describe it quickly becomes more unusual with the next sentence. It is elongated. It spins with startling speed, completing a rotation in only about 4 hours. It has 2 moons. It has a ring. It is associated with the only widely discussed collisional family in the Kuiper Belt. Its surface appears unusually rich in water ice. Its shape and density raise questions about internal structure, equilibrium, and the mechanical behavior of icy material under rapid rotation. In short, Haumea is one of those worlds that seems less like a single answer than a cluster of linked questions. If Pluto is the case for complexity arising in an unexpectedly active dwarf planet, Haumea is the case for complexity arising in a body whose whole system may preserve the memory of some dramatic event, or events, in the Kuiper Belt's past. There are several formation ideas in circulation. Perhaps Haumea suffered a giant impact that stripped away part of an icy mantle and left behind a rapidly spinning, elongated remnant. Perhaps multiple collisions were involved. Perhaps rotational fission played some role. The exact scenario remains unsettled. That lack of final agreement is not a weakness in the story. It is the story. Haumea matters because it sits at the intersection of several major Kuiper Belt themes at once: collision, spin, differentiation, satellites, rings, and family formation. If the Kuiper Belt is a record of early solar system processes, Haumea is one of the places where the record seems smudged, but still legible enough to be tantalizing. Its associated family members appear dynamically clustered and are notable for strong water ice signatures, suggesting a shared past. And yet, reconstructing that past has proved difficult. The size distribution, velocity spread, and present characteristics of the family do not surrender a single universally accepted explanation. I find that oddly restful. Not the uncertainty itself, perhaps, but the way it reminds us what science really looks like in frontier regions. A distant world is observed in partial light. Its spin is measured. Its shape is inferred. Occultations reveal more. Spectra add another layer. Moons are detected. A ring appears. Family members are debated. Models are proposed, tested, revised. The object does not become less interesting as the case grows more complicated. It becomes more itself. And Haumea is not merely a curiosity, it is informative. A ring around such a distant dwarf planet raises questions about the formation and stability of ring systems around small icy bodies. Its rapid spin prompts questions about how icy materials behave under stress and whether a body that size can truly conform to simple equilibrium expectations. Its water-rich surface pushes us to ask how old surfaces weather in the Kuiper Belt, how resurfacing might occur, and what collisions do to composition and texture. Its family, if indeed a true collisional family, may preserve one of the clearest large impact signatures we have in the outer solar system. One eccentric world, many doors. There is also a deeper philosophical appeal in Haumea's oddness. The largest planets often dominate public imagination because of scale, but the small and medium worlds are where the solar system's improvisation shows most clearly. They do not all fit the tidy textbook silhouettes. Some spin too fast. Some keep moons in surprising arrangements. Some carry rings where one might not have expected rings. Some look as though they were assembled softly. Some look as though they survived violence. The Kuiper Belt is rich in such irregular biographies. Makemake and Eris contribute to that richness in their own ways. Eris, residing in the scattered population, is slightly more massive than Pluto, and was one of the discoveries that forced the planetary definition issue into the open. Makemake adds another large dwarf planet to the outer census, one with its own surface and satellite story. Taken together with Pluto and Haumea, these bodies show that the Kuiper Belt is not a minor appendix to the solar system. It is one of the places where planetary science becomes comparative in a particularly revealing way. Here are multiple dwarf planets, all formed in broadly similar outer conditions, and yet each carries a distinct evolutionary path. It can be soothing, after the strangeness of Haumea, to step back and consider the whole region again from a distance. Imagine looking not at one world, but at the broad sweep beyond Neptune. A layered outer system with karma bands, resonant bands, scattered populations, rare giant members, many small ones, binaries here, family fragments there, and a very long tail of bodies still too faint to know intimately. It is less like a single shelf of identical files, and more like an archive annex built in stages, where some drawers are orderly, some overstuffed, and some contain materials from earlier rearrangements that no one entirely documented at the time. That feeling of partial order is part of the science. The Kuiper Belt is not supposed to be completely neat. In fact, if it were neat, it would tell us less. Its complexity is evidence that the solar system had a dynamic youth. Planets migrated, resonances swept. Some materials remained local, some were transported, some were lost. The outer regions were not left outside history. They were written by it. If one were to ask what the Kuiper Belt tells us about planet formation more generally, the answer would begin with leftovers, but could not end there. The belt is the remnant of a population that never turned itself efficiently into one or more full-sized outer planets. That inefficiency is itself informative. In the inner solar system, material could accrete into terrestrial planets. In the region of the giant planets, cores grew large and then accumulated gas. But in the distant outer reaches beyond Neptune, growth was slower. The density of material was lower. Timescales were longer. Neptune's influence became disruptive. Much of the original mass appears to have been removed, scattered, or ejected over time. The modern belt is only a fraction of what formation models suggest may once have existed there. That discrepancy between the belt we see now and the more massive outer disk many models require is another important clue. It implies depletion. Something happened to thin the population dramatically. Migration and scattering provide much of the explanation. Some bodies were thrown inward and then outward by giant planet dynamics. Some were lost to the Oort cloud. Some were ejected from the solar system entirely. Some collided and fragmented. The quiet, frozen frontier we see now is not the full original inventory. It is the survivor list. Survivor lists are interesting documents. They do not show everything that once existed. They show what endured, and endurance is selective. A resonant body endured differently from a cold classical. A scattered object endured differently from a detached one. A binary endured under conditions that did not destroy it. A contact binary endured under conditions that did not tear it apart. A dwarf planet endured as something large enough to keep geological and chemical possibilities alive. The modern Kuiper Belt is, in that sense, a biased but revealing archive. Its biases are part of the message. There is an almost ecological quality to that idea. Not ecology in the biological sense, of course, but in the sense of niches, pressures, survivals, and population structure. Some kinds of worlds endure best in certain dynamical environments. Some histories remain legible only where later disturbance was limited. Some pathways lead inward toward the centaurs and comets. Some end in long-term stable resonances. The belt has neighbourhoods, and the neighbourhoods matter. We should also say a word about the difficulty of studying all this, because the challenge is part of the science. Kuiper Belt objects are faint, very faint. Their distance dims them brutally, and most are only detectable because they reflect a small portion of sunlight. Many of the most interesting bodies are points of light, even in powerful telescopes. Rotation periods are extracted from subtle variations in brightness. Sizes often depend on albedo assumptions unless thermal measurements or occultations improve the estimate. Spectra are hard won. Surface maps are mostly impossible for all but the largest few, and even then they are coarse from Earth-based observations. Much of Kuiper Belt science consists of turning small signals into durable inferences. That reality gives the field a certain elegance. Astronomers do not often receive complete portraits from this region. They receive hints. A light curve suggests elongation or an albedo patch. A spectrum hints at water ice or methane. An occultation refines shape or reveals a ring. A binary orbit gives a system mass. Over time, the hints accumulate. One of the pleasures of the Kuiper Belt is that it rewards patience not only in its discovery, but in its interpretation. Occultations, in particular, have become a quiet triumph of outer solar system science. When a distant object passes in front of a star, the starlight briefly dims or disappears from certain viewing locations, allowing astronomers to infer the object's size, shape, and sometimes atmosphere or ring structures with remarkable precision. It is a beautifully indirect method, rather like deducing the outline of a moving key by the shadow it casts across a distant wall. Some of the most informative details about bodies such as Haumea have come not from direct imagery, but from this kind of fleeting alignment. The outer solar system often advances by such means, not by grand display, but by careful geometry. There is a kind of humility built into those methods. You do not see the whole world. You infer its dimensions from a momentary dimming of a distant star. You do not step on the surface. You estimate its composition from the wavelengths of light it reflects. You do not watch a billion-year history unfold. You reconstruct it from an orbit, a resonance, a spin rate, a family of fragments, a subtle redness in a spectrum. Kuiper Belt science is full of restrained conclusions, and that restraint is part of what makes it trustworthy. It also means that every now and then, when a direct observation does arrive, it feels unusually rich. New Horizons at Pluto and then Arakoth did not simply add pictures. It gave scale to imagination. It helped everyone working on the region calibrate what a point of light might conceal. A distant KBO might be mundane by planetary standards, but it might also have ridges, pits, layering, a delicate merger shape, a strange distribution of frost, or signs of a surprisingly coherent formation story. One lesson of planetary science is that low resolution often makes worlds seem simpler than they are. I think that is part of why the Kuiper Belt works so well as a subject for a quiet case file. The belt itself is an argument against thinking that what matters most must also be what shines most brightly. The region is dark, cold, sparse, and observationally difficult. Yet it speaks to some of the largest questions in planetary science. How did the solar system form? Did the giant planets move substantially after formation? How do resonances trap bodies? How do small icy worlds evolve? Where do short-period comets come from? How common are binaries, rings, and collisional families in distant populations? What is preserved from the primordial disk, and what has been rewritten by later dynamics? Those are not fringe questions, they are central questions. They just happen to be answered, in part, by worlds that spend most of their lives in shadow. There is also the matter of scale, which is easy to lose when talking about a region this remote. The main body of the Kuiper Belt begins beyond Neptune, around 30 astronomical units from the Sun, and extends to around 50 astronomical units, with the scattered populations carrying the story much farther outward. That means sunlight there is weak, temperatures are low, and orbital periods are long. A body at roughly 40 astronomical units can take around 250 years to complete a single orbit. Human institutions change, nations rise and fall, scientific theories are born and refined, and these small worlds have barely shifted one part of their path. The pace is not merely slow by human standards. It is another category of time. Slow time changes how one thinks about cause and effect. A resonance that appears abstract in a diagram is actually a stable pattern maintained over spans of time so long that history begins to feel too small a word. A scattered object may spend ages climbing outward and returning again. A collisional family, if real, may preserve the outcome of an event older than most features on Earth's surface. The belt is calm, not because nothing happens, but because what happens often unfolds across intervals that humble narration. There is another form of slow time out there as well, the time of seasons on distant worlds. Pluto, for example, takes so long to orbit the Sun that its seasonal cycles are immense compared with Earth's. Frosts migrate. Thin atmospheres can expand and contract. Illumination angles change on timescales that would feel almost geological to us. Even where there is activity, it is measured in drawn-out transitions rather than sudden daily weather. The Kuiper Belt can therefore feel doubly distant, distant in space and distant in tempo. Even erosion works differently there. The belt slowly erodes away. Collisions produce fragments. Dust can be carried off. Objects are occasionally perturbed inward. This is not the dramatic erosion of cliffs under wind and rain. It is a celestial erosion, sparse and patient. A region can diminish without ever seeming hurried. And yet the belt is not dead. One must be careful with words like fossil and archive, useful though they are. The Kuiper Belt preserves the past, yes, but it also participates in the present. It still supplies centaurs. It still contributes to the Jupiter family comets. It still contains surfaces being weathered, binaries maintaining their orbits, rings circling dwarf planets, and bodies moving through resonances with perfect, indifferent timing. An archive that still occasionally dispatches messengers inward is not a sealed archive. It is worth returning, briefly, to the question of why the belt did not simply produce another planet. This is one of the quiet premises beneath the whole story. In the early outer solar system, one might imagine that if enough material existed beyond Neptune, it could have gathered into yet another large planet. But accretion in the distant solar system is slow, because orbital speeds are lower, material is less dense, and collision timescales are long. Add to that the disruptive influence of Neptune's migration and scattering, plus the later depletion of the region, and large-scale planet building becomes inefficient. The Kuiper Belt is what remains of a place where planetesimals formed, but planetary completion did not proceed in the same way it did elsewhere. That unrealized possibility gives the belt a subtle poignancy. It is a record not only of what formed, but of what failed to finish forming. The region is full of partial stories, arrested growth, interrupted accretion, fragments of a construction project that the solar system never completed in that location. Yet those incomplete results are precisely what make the belt so informative. A fully built planet would have overwritten much of the record. A belt of leftover worlds still keeps it. So the belt occupies an unusual middle ground in the architecture of the solar system. It is not as geologically rich, on average, as the major planets. It is not as dynamically raw as an unprocessed primordial disk. It is not as distant and isotropic as the Oort cloud. It is a surviving outer population with enough history to be structured and enough preservation to remain revealing. It is transitional in location and transitional in meaning, bridging planet formation, small body science, and cometary supply. This also makes it an unusually useful comparison point. The asteroid belt, closer to the Sun, is rocky, hotter, more collisionally processed in some ways, and strongly shaped by Jupiter. The Oort cloud, much farther out, is a vast distant reservoir whose members are only known indirectly through the comets they send inward. The Kuiper Belt sits between those cases, both physically and conceptually. It is cold enough to preserve abundant ices, near enough to be surveyed, organized enough to reveal migration signatures, and active enough to feed objects inward. It is the outer solar system's most readable intermediate chapter. One can feel that bridge most clearly in the comets. A short-period comet entering the inner solar system is not simply a visitor from nowhere. In many cases, it is the latest dynamical chapter of an object that may have spent billions of years beyond Neptune, then been scattered inward through the Centaur phase, then captured into a shorter period orbit by Jupiter. By the time we see the tail and coma, the body is already well into a transformed late life. The luminous spectacle is the result of solar heating acting on a small, icy body that originated in deep cold. Comets, in that sense, are not only solar system debris. They are Kuiper Belt narratives made briefly visible. That thought makes the region feel less remote. We tend to divide the solar system into near and far, inner and outer, visible and obscure. But the Kuiper Belt leaks inward through dynamics. It is connected to us by transfer routes, however slow and selective. Some near-Earth objects may even be dormant, burned-out comets, whose deeper origin lies in that distant belt. The outer archive is not locked. The more one studies the Kuiper Belt, the more it also becomes a comparative tool for planetary systems beyond our own. Around other stars, astronomers see debris disks, belts of coal dust, and hints of planetesimal populations shaped by planets. Our own Kuiper Belt becomes a local example through which broader questions can be asked. What does an outer small body belt look like after billions of years of planetary sculpting? How do migrating planets imprint resonances and depleted zones in leftover populations? How many planetary systems carry their formation history in cold outer belts that we can only partly resolve? The Kuiper Belt is both local evidence and a model system. That exoplanet connection has a pleasant way of enlarging the room. For a while, the Kuiper Belt seemed like an obscure appendix to our own solar system, a remote belt of interest mainly to specialists in comets and dwarf planets. But once astronomers began discovering debris disks and planetary architectures around other stars, our distant icy belt started to look more universal in spirit. Perhaps many planetary systems end up with some outer archive of leftovers, rearranged by giant planets, ground down by time, and visible only indirectly. If so, then the Kuiper Belt is not merely a local curiosity. It is a nearby example of a broad planetary theme. It is tempting, at this point, to call it the solar system's attic, and perhaps that metaphor is not entirely wrong. But attics imply neglect, and the Kuiper Belt is better than neglected. It is curated by gravity. The cold classicals were left in relative peace. The resonant populations were arranged into repeating patterns. The scattered disk was flung wide. Detached objects were left in more cryptic states. Pluto became a recognized representative of a larger class. Haumea became the eccentric folder with too many annotations in the margin. Even the centaurs function like documents checked out from the archive and sent inward on temporary loan. Back in my office, I can almost see the analogy in the circle of lamplight and the colder dark beyond it. Here near the centre, close to the warmth, everything changes quickly. Paper curls, coffee cools, dust shows itself. Farther out, on the shelf beyond the easy reach of the light, things stay as they were for longer. Not unchanged forever, but preserved in a quieter way, altered by long intervals rather than busy hands. The Kuiper Belt is like that shelf. Not pristine, not untouched, but slower to surrender its evidence. And maybe that is why it feels so restful to think about. The inner solar system is full of urgency by comparison. Worlds close to the sun are heated, resurfaced, atmospherically stripped, volcanically active, tectonically revised, impact-scarred, and often overprinted. The Kuiper Belt, for all its dynamical history, still allows some things to remain legible. A binary can persist. A resonance can endure. A surface can retain the chemistry of deep cold. A contact binary can survive with its gentle shape. Even a strange fast-spinning dwarf planet can keep clues to an old collision alive in its ring, moons, and family. There is humility in that. We are reading a region not because it came out neat, but because enough of it was not erased. One day, of course, we may know far more. Better surveys will expand the inventory. More occultations will sharpen sizes and shapes. Telescopes can probe surface compositions of selected large KBOs in greater detail. Ground-based surveys continue to improve orbital classifications and population statistics, and perhaps in time, another spacecraft will head outward, to Haumea or another large KBO, or to some object not yet famous enough to have a public constituency. New Horizons already proved that a flyby at Kuiper Belt distances can revolutionize understanding. The next mission, whenever it comes, will likely do the same. There is something moving about that future work, because outer solar system exploration is always an act of patience. Missions take years to launch, years more to travel, and then only a brief encounter to collect the data that scientists will study for decades afterward. The Kuiper Belt almost trains human institutions to become more patient than usual. You cannot rush 40 astronomical units. You cannot negotiate with orbital mechanics. You send the spacecraft, you wait, and you let the solar system keep its schedule. But even without another spacecraft tomorrow, the essential shape of the case is already beautiful. The Kuiper Belt is a leftover population from the solar system's formation, preserved beyond Neptune in a broad icy region. Its present structure reflects the migration and gravitational influence of the giant planets, especially Neptune. Its populations include calm, cold classicals, more excited hot classicals, resonant bodies such as Pluto and the Plutinos, scattered objects on elongated tilted paths, and derivative inward migrants such as the centaurs. It holds large dwarf planets, binaries, moons, rings, strange surfaces, and possible collisional families. It is a major source of many short-period comets, and it remains one of the best surviving records of how the outer solar system became what it is. That is the clean summary, but the slower version is better. The slower version says that beyond Neptune, in weak sunlight and vast orbital years, there exists a region that keeps old motions stored in cold form. Some of its worlds seem to have stayed close to where they formed. Some were nudged, captured, and refiled into resonances. Some were scattered into long, lonely ellipses. Some may have struck one another hard enough to create whole families. Some retained companions. Some developed rings. Some drift inward and become, for a little while, comets bright enough for us to notice from Earth. A population once inferred from the logic of cometary orbits has become a landscape of many different histories, all bound together by distance, ice, and the long hand of Neptune. The mug beside my notes has cooled now. The steam is gone. The room feels quieter than it did when I opened the file, as though order has arrived not by simplifying the case, but by giving each piece its proper place. That is usually the best kind of understanding, not the kind that reduces a subject to one slogan, but the kind that lets every strange detail remain strange, while still belonging to a larger pattern. The Kuiper Belt allows that kind of understanding. It can be described as a donut-shaped region of icy bodies beyond Neptune, and that is true. It can be described as a source of short-period comets, and that is also true. It can be described as a remnant of planet formation and a record of giant planet migration, and that too is true. But none of those sentences alone feels large enough. The belt is all of them together. A remnant, a record, a reservoir, a set of populations, a dynamical map, a quiet supplier of future comets, and a home to some of the most unexpectedly revealing worlds in the solar system. So I will close the folder gently on that thought. Not that the case is finished, exactly. Cases like this are never finished. New objects are found. Better measurements arrive. Old models are tested against new data. But the broad picture has settled enough to be comforting. There is order beyond Neptune. Not simple order, not static order, but the kind that emerges when a planetary system leaves traces of its past in the orbits of small worlds. And far out there, in the cold outer dark, those worlds keep circling. The cold classicals continue their quiet paths. The Plutinos remain in rhythm with Neptune. Scattered objects climb and fall along drawn-out ellipses. Haumea spins rapidly through the black with its moons and ring. Pluto keeps its measured relation to Neptune, crossing no dangerous threshold despite appearances. Small fragments collide, dust drifts, centaurs are supplied. Comets begin the first stages of a journey inward. The archive remains active, but never hurried. Outside my window, the sky is only a dark pane tonight, with no hint of that distant frontier except what the mind can place there. But that is enough. Somewhere beyond the last giant planet, beyond the easy naming of the classical planets, beyond where sunlight still counts as generous, the solar system keeps one of its quietest records. A belt, yes, though not quite a belt. A frontier, yes, though not an empty one. A region of leftovers, certainly, but leftovers that never stopped mattering. And now, as the lamplight softens over the closed file, we can leave the Kuiper Belt where it belongs for the moment. In the far cold outer shelves of the solar system, still holding its evidence, still turning slowly, still making the case that what survives at the edges can tell us how the whole story was made.